On the morning of March 10, 1906, the Courrières mining complex in northern France operated according to established industrial practice. Over 1,800 men descended into a network of interconnected shafts and galleries spanning multiple pits. Ventilation systems circulated air through designated pathways. Supervisors monitored for visible signs of fire damp accumulation. Coal extraction proceeded on schedule. Within minutes of an underground ignition event, approximately 1,099 miners would be dead. The catastrophe would become the deadliest mining disaster in European history. Yet the system had not malfunctioned. It had performed precisely as its design permitted. The Courrières complex exemplified early 20th century mining ventilation philosophy: continuous through-flow, minimal dead zones, optimized for fire damp dilution. The shafts were interconnected in ways that facilitated production logistics, but also created unobstructed propagation pathways for pressure waves and toxic gases. Detection of underground combustion depended on sensory observation by workers already inside the hazard zone. The failure was not operational error. It was architectural. The same connectivity that enabled efficient coal movement enabled efficient transmission of explosive force. The same ventilation flows that sustained working conditions distributed combustion products across kilometers of tunnels. The system's assumptions about incident scale, detection capability, and evacuation timing were invalidated the moment ignition exceeded localized parameters. This is an analysis of how industrial design philosophy, embedded in shaft geometry and emergency doctrine, predetermined the scope of fatality before any flame appeared. How does a ventilation system designed to sustain life become the primary mechanism for distributing death? To answer that question requires understanding what the Courrières complex was designed to accomplish, and what assumptions its designers embedded into every shaft, every airway, and every operating procedure. The mining infrastructure that existed in March 1906 was not primitive by the standards of its era. It represented the accumulated engineering knowledge of French coal extraction, optimized over decades for a specific set of objectives. Those objectives and the trade-offs they required created the physical and organizational architecture within which the disaster became not merely possible, but structurally inevitable. The Courrières mining concession operated 4 primary extraction pits in the Pas-de-Calais coalfield: Pit 2 at Billy-Montigny, Pit 3 at Méricourt, Pit 4 at Salamines, and Pit 10 at Billy-Montigny. These were not independent operations. The underground workings of all 4 pits were interconnected through a network of galleries, haulage routes, and ventilation airways that extended over 110 kilometers in total length. Coal, extracted from one pit, could be transported underground to another pit's hoisting shaft. Air circulated through the entire network according to pressure differentials maintained by surface ventilation fans. From an engineering perspective, the 4 pits functioned as a single atmospheric system. This connectivity was not accidental. It was the deliberate result of design philosophy that prioritized extraction efficiency and ventilation effectiveness. The French mining industry of the early 20th century understood fire damp, methane gas released from coal seams, as the primary underground hazard. Methane is explosive at concentrations between 5 and 15% in air. The solution, refined over generations, was continuous dilution, maintains sufficient airflow through all working areas to keep methane concentrations below dangerous thresholds. This required large volumes of fresh air, delivered reliably to every active face, and exhausted efficiently to prevent accumulation in dead-end passages. The physics of underground ventilation favor connectivity. A single large fan can move air through an extensive network more efficiently than multiple small fans serving isolated sections. Connecting galleries between pits allows air to flow through the path of least resistance, equalizing pressure and ensuring continuous movement. The alternative, isolated ventilation circuits for each pit, would require more infrastructure, more maintenance, and more energy consumption while delivering less reliable airflow to working faces. From the perspective of fire damp management, the interconnected design was superior. But this design philosophy embedded an assumption that would prove fatal, that the hazards ventilation was designed to address, specifically localized methane accumulation, represented the full scope of atmospheric risk. The interconnected network was optimized for dilution of a gas that accumulated gradually and could be detected by trained observers using flame safety lamps. It was not designed for rapid isolation during a propagating combustion event. No mechanism existed to segment the network into independent atmospheric zones. No barriers could be closed to prevent pressure waves or toxic gases from traveling through the same pathways that normally carried fresh air. The ventilation infrastructure at Courrières included intake shafts that drew fresh air from the surface, distribution galleries that directed airflow to working areas, and return airways that carried exhaust air to upcast shafts equipped with furnaces or mechanical fans. The system operated on the principle of continuous flow. Air entered at designated points, traveled through the workings, and exited at designated points, maintaining a pressure differential that ensured consistent movement. This design worked exactly as intended under normal conditions. It failed catastrophically when conditions departed from normal because it had no mechanism for responding to abnormal conditions. The second embedded assumption concerned the nature of underground fires. Fire was a recognized hazard in coal mines, and the Courrières operation had established procedures for fire response. These procedures reflected experience with localized combustion events, fires that started in timber supports, in coal accumulations, or in areas where frictional heat from equipment ignited combustible material. Such fires developed gradually. They produced visible smoke and detectable heat. They could be approached, assessed, and either extinguished or isolated by constructing barriers to starve them of oxygen. The procedures assumed that fire remained a local phenomenon, bounded by the physical space in which combustion occurred, and that responders would have time to evaluate the situation and implement countermeasures. This assumption failed to account for the explosive potential of coal dust. While fire damp had been the focus of ventilation design and safety training, coal dust represented a different category of hazard, one that was understood in laboratory settings but not operationally integrated into mine safety practice. Coal dust, when suspended in air at concentrations above approximately 40 grams per cubic meter, forms an explosive mixture. The ignition energy required is low, the deflagration velocity is high. And critically, the explosion itself entrains additional dust from surfaces, creating a self-sustaining chain reaction that can propagate through any space containing sufficient accumulated dust. The galleries of the Courrières complex contained substantial coal dust accumulation. Haulage routes, where coal cars traveled continuously, were particularly affected. Dust settled on floors, walls, and timber supports. It accumulated in crevices and along rail lines. Dust suppression, typically water spraying, was practiced inconsistently, primarily to manage visibility and respiratory comfort rather than to eliminate explosion risk. The economic incentive structure did not prioritize dust control. Wetting operations consumed time and resources that could otherwise be devoted to extraction. As long as fire damp concentrations remained acceptable, the mine was considered safe to operate. This created a physical condition invisible to the safety framework, kilometers of gallery lined with explosive fuel, connected by airways that would transmit any ignition event throughout the network. The design assumption that fire remained local was valid only for fires that did not interact with this fuel. A fire that reached the dust became something categorically different, not a local combustion event, but a propagating detonation with network-wide reach. The detection methodology reinforced this blind spot. Underground hazard detection at Courrières relied almost entirely on human sensory observation. Miners carried flame safety lamps, Davy lamps, or their derivatives, that provided illumination while also serving as crude methane detectors. In the presence of fire damp, the lamp flame would elongate and change color before the surrounding atmosphere reached explosive concentration. Trained miners could interpret these signals and take appropriate action, typically withdrawing and reporting the accumulation. This detection method was effective for its intended purpose, identifying localized methane buildup before it reached dangerous levels. But the safety lamp could not detect coal dust concentration. Dust was visible as a general atmospheric condition. Miners knew when they were working in dusty areas, but no quantitative measurement existed. No threshold concentration triggered alarm. No procedure specified evacuation based on dust levels. The hazard was present throughout the mine, visible in the ordinary course of operations, yet invisible to the safety system because the safety system was not designed to see it. Similarly, fire detection depended on sensory observation. Smoke, heat, and the smell of combustion were the primary indicators. These signals propagated slowly compared to the speed at which a dust explosion could develop. A fire that had been burning for hours or days produced observable effects at considerable distance. A dust explosion propagated at hundreds of meters per second, far faster than any sensory signal or human response. The detection methodology assumed incident development rates compatible with human perception and reaction times. Coal dust explosions violated this assumption by orders of magnitude. The physical layout of the Courrières complex compounded these vulnerabilities. The 4 pits were connected not merely for ventilation purposes, but for operational efficiency. Underground haulage routes allowed coal to be transported to whichever pit had available hoisting capacity. Personnel could move between pit sectors through connecting galleries. This connectivity meant that any atmospheric event in one pit could reach all other pits through direct physical pathways. The underground workings formed a single connected volume with no internal barriers capable of preventing gas flow or pressure transmission. The design also reflected economic optimization that traded redundancy for efficiency. A single ventilation network serving all pits cost less to construct and operate than multiple independent systems. Shared haulage infrastructure reduced the need for duplicate equipment at each pit. Centralized management of airflow allowed rapid adjustment to changing extraction patterns. These efficiencies made the Courrières operation commercially competitive. They also meant that a failure anywhere in the system could propagate everywhere in the system. The emergency response architecture exhibited the same characteristics. Evacuation procedures assumed localized incidents requiring withdrawal from affected areas to unaffected areas within the mine. The concept of simultaneous network-wide emergency was not operationally planned because the design assumptions did not admit its possibility. No unified alarm system could alert all 4 pits simultaneously. Communication between pit bottoms and surface relied on signal bells and, in some cases, voice tubes, methods adequate for routine coordination, but incapable of transmitting urgent warnings across the entire complex within the time frame required by a propagating explosion. Understanding these design parameters is essential because they determined what the disaster could become before any ignition occurred. The Courrières complex was not unsafe by the standards and knowledge of its era. Its ventilation was effective. Its fire damp management was competent. Its operational practices reflected accumulated industry experience. But the system was optimized for a hazard model that did not include network-wide dust explosions. Every design choice that improved efficiency for normal operations, connectivity, through-flow ventilation, shared infrastructure, centralized management, simultaneously created the conditions for catastrophic failure when the hazard model proved incomplete. The system's designers were not negligent. They built what their understanding of underground hazards indicated was necessary. The gap was epistemic. Coal dust explosion mechanics were not yet integrated into operational safety practice, even though laboratory research had demonstrated the phenomenon. The translation from scientific understanding to engineering implementation had not occurred. The Courrières complex embodied the state-of-the-art in fire damp management while remaining structurally vulnerable to a hazard its designers had not been trained to address. This is the foundational premise of the disaster, a system designed competently for one hazard model. operating within a physical environment that included a different hazard entirely. The ventilation network that protected miners from methane poisoning would become the transmission infrastructure for a dust explosion. The connectivity that ensured reliable airflow to every working face would ensure reliable distribution of toxic afterdamp to every connected gallery. The design intent, to sustain life through continuous fresh air supply, would be inverted by an event the design did not anticipate. The next stage of analysis must examine how operational culture, training emphasis, and economic incentives interacted with these physical vulnerabilities. The design created the possibility of catastrophic failure. Human factors determined whether that possibility would be realized. The physical architecture of the Courrières complex created the conditions under which catastrophic failure was possible. But architecture alone does not cause disasters. The translation from latent vulnerability to realized catastrophe requires human action or inaction, guided by training, incentive structures, and institutional priorities that determine how people perceive and respond to risk. In the days and hours preceding March 10, 1906, every decision made by Courrières management and supervisory personnel was rational within the framework they had been given. That framework, however, contained systematic blind spots that aligned precisely with the physical vulnerabilities embedded in mine design. The operational culture at Courrières reflected broader patterns in early 20th century French coal mining. The industry operated under economic pressure to maximize extraction while minimizing cost. Coal was essential to industrial production, and demand consistently exceeded supply. Mining companies competed for market share and profitability. Within this environment, operational decisions balanced safety considerations against production imperatives, not because managers were indifferent to worker welfare, but because the economic structure rewarded output and penalized disruption. A mine that ceased production lost revenue. A mine that maintained production, even under marginal conditions, remained viable. This economic logic shaped how risk was assessed and communicated throughout the organizational hierarchy. Supervisors who halted operations for uncertain hazards faced questions about lost production. Supervisors who maintained operations and avoided incidents were rewarded for sound judgment. The incentive structure systematically favored continuation over precaution in ambiguous situations. When hazard indicators were clear and unambiguous, explosive fire damp concentrations, visible structural failure, immediate danger, procedures mandated withdrawal and remediation. When indicators were ambiguous or gradual, a smoldering fire in an isolated area, elevated but not explosive gas readings, dust accumulation along haulage routes, the default response was monitoring rather than evacuation. This default was not irrational. Mining operations routinely encountered minor anomalies that resolved without intervention. Overcautious response to every variation would render extraction economically impossible. Experienced supervisors learned to distinguish between conditions requiring immediate action and conditions that could be safely monitored. The problem was that this learned discrimination was calibrated to the hazard model embedded in training, primarily fire damp management, rather than to the full range of physical hazards present in the mine. Supervisors became skilled at assessing methane risk while remaining systematically undertrained in recognizing conditions that could trigger coal dust explosions. The training regime at Courrières emphasized fire damp detection and response as the primary underground safety competency. Miners learned to read safety lamp behavior, to recognize the characteristics of methane accumulation, and to report elevated readings through established channels. They understood the explosive range of fire damp and the importance of ventilation in maintaining safe atmospheric conditions. This training was effective for its intended purpose. Fire damp incidents at Courrières were rare relative to extraction volume, indicating that the detection and response system functioned as designed. Coal dust, by contrast, received minimal attention in safety training. Miners were aware of dust as an occupational nuisance. It impaired visibility, caused respiratory irritation, and accumulated on equipment and surfaces. Dust suppression was practiced primarily for these practical reasons rather than as explosion prevention. The connection between suspended dust and explosive potential was not part of standard safety education. Workers who spent their shifts surrounded by coal dust did not understand that they were working within a fuel-air mixture, awaiting only an ignition source. This training gap reflected the state of knowledge transfer between research and operations. Laboratory experiments had demonstrated coal dust explosivity decades before 1906. The phenomenon was documented in scientific literature and discussed in mining engineering circles. But the translation from laboratory finding to operational practice had not occurred systematically. Safety regulations focused on fire damp because fire damp explosions were frequent, well understood, and directly attributable to measurable atmospheric conditions. Coal dust explosions were rarer, often misattributed to fire damp, and not associated with easily measurable thresholds. The regulatory framework had not caught up with the science, and operational training reflected regulatory priorities. The human factors implications of this gap were profound. Supervisors making real-time decisions about mine safety possessed mental models that accurately represented methane hazards but systematically underweighted dust hazards. When they assessed whether conditions were safe for continued operations, their assessment framework excluded the mechanism that would ultimately cause catastrophic failure. This was not negligence, it was the predictable consequence of training aligned with an incomplete hazard model. The days immediately preceding March 10th illustrated how this framework operated in practice. On March 7, 1906, a fire was discovered in the Cecile Gallery of Pit 3. The fire appeared to involve timber supports and accumulated coal debris in a section of the mine not currently in active extraction. Initial assessment indicated a localized combustion event, concerning but containable. Management faced a decision: evacuate the entire interconnected complex and halt production until the fire was fully extinguished, or continue operations while monitoring the fire and implementing containment measures. The decision to continue operations was consistent with established practice and the information available at the time. The fire was not near active working phases. Ventilation could be adjusted to direct smoke away from occupied areas. Monitoring parties could observe the fire's behavior and report any escalation. Production could continue in unaffected sections while remediation proceeded in the affected area. This approach had succeeded in previous instances of underground fire at Courrières and throughout the French mining industry. The protocol assumed that fires remained bounded phenomena, developing gradually enough to permit assessment and response. What the protocol did not account for was the fire's potential interaction with the dust-laden atmosphere of the connected galleries. The fire itself was a localized heat source. The galleries surrounding it contained accumulated coal dust. The ventilation system, continuing to operate normally, moved air through the network, air that could suspend dust and carry heat. The conditions for a dust explosion were assembling, while management's attention remained focused on the visible fire and its immediate surroundings. The decision framework also reflected organizational dynamics that discouraged precautionary evacuation. Evacuating over 1,800 workers from 4 interconnected pits would halt production across the entire Courrières operation. The economic impact would be substantial. If the fire proved containable, as most underground fires did, the evacuation would appear, in retrospect, to have been an overreaction. Supervisors and managers who ordered unnecessary evacuations faced reputational and professional consequences. The incentive structure favored continued operations unless danger was immediate and unambiguous. This bias was reinforced by the information flow within the organization. Reports from monitoring parties described the fire's visible characteristics: location, approximate size, smoke production, perceived trajectory. These reports did not include, because no measurement existed, coal dust concentrations in surrounding galleries or the fire's proximity to explosive fuel-air mixtures. The information reaching decision-makers was filtered through a framework that captured some hazard dimensions while omitting others. Decisions made on this basis were logical given the information provided, yet systematically miscalibrated to the actual risk. Communication infrastructure compounded the problem. The Courrières complex had no centralized alarm system capable of warning all underground personnel simultaneously. Communication between surface and pit bottom relied on signal bells, effective for routine coordination but inadequate for emergency notification. Communication between different pits underground was even more limited, depending on messengers traveling through connecting galleries. In a rapidly developing emergency, this communication architecture could not transmit warnings faster than the emergency itself propagated. The shift handover process on the morning of March 10th illustrated these limitations. Night shift personnel had monitored the fire in Pit 3 and found it stable. Day shift personnel received reports indicating continued fire presence but no escalation. The information conveyed was technically accurate. The fire had not visibly expanded, but omitted context that might have prompted different decisions. No discussion of dust conditions in connecting galleries. No assessment of whether ventilation patterns might be transporting ignitable material toward the heat source. No consideration of scenarios in which a stable fire could suddenly interact with explosive atmosphere. The 1,800 men who descended into the Courrières complex on the morning of March 10 did so believing they were entering a workplace with a known, monitored, and controlled hazard. Their supervisors believed the same. Management believed the fire presented an ongoing concern, but not an immediate threat to personnel working in unaffected areas. Every level of the organization operated from a shared mental model in which the fire was a localized problem being actively managed. This mental model was not wrong about the fire itself. It was wrong about what the fire could become when combined with atmospheric conditions outside its immediate perimeter. The gap between the model and reality was invisible because the information systems, both technical and organizational, were not designed to detect it. The alarm and indication systems available to Courrières operators reinforced this gap. The primary atmospheric monitoring tool, the flame safety lamp, could detect fire damp but not coal dust concentration. Even if supervisors had been trained to consider dust hazards, they possessed no instrument capable of quantifying the risk. The absence of measurement capability translated into absence of operational awareness. Hazards that cannot be measured are hazards that cannot be systematically managed. The alarm system itself was designed for the communication technology of its era. Signal bells and voice tubes could transmit simple messages, all clear, assistance needed, evacuation, but could not convey complex situational information. The alarm architecture assumed that supervisors at each pit would make independent assessments based on local conditions and coordinate through established protocols. It did not assume, because the design philosophy did not include, situations in which all pits would require simultaneous evacuation faster than the communication system could operate. Human factors analysis of the Courrières disaster must therefore identify not individual failures, but systematic patterns that made certain failures probable. The training regime emphasized fire damp while neglecting dust. The decision framework favored production continuity in ambiguous situations. The economic structure penalized precautionary shutdowns. The information systems filtered out precisely the data needed to recognize dust explosion risk. The communication infrastructure could not support rapid network-wide emergency response. Each of these factors, individually, represented a reasonable adaptation to operational constraints. Together, they created an organizational system that would systematically misread the hazard present in early March 1906. The fire in Pit 3 was the proximate latent condition. The ultimate latent condition was the set of assumptions, incentives, and information structures that determined how the organization would perceive and respond to that fire. Given these conditions, the decision to continue operations was not merely predictable, it was the only decision the system was configured to produce. Alternative decisions, precautionary evacuation, production halt, comprehensive atmospheric assessment would have required information the system did not collect, training the workforce had not received, and incentives the organization did not provide. Understanding this is essential because it reframes the question of responsibility. The disaster was not caused by individual negligence or incompetence. It was caused by systematic gaps between the hazard present in the physical environment and the hazard model embedded in organizational practice. The people who made decisions on March 7, 8, 9, and 10 were acting rationally within their framework. The framework itself was miscalibrated to reality in ways that the individuals operating within it could not see. The stage was now set for the initiating event. A fire burned in Pit 3. Over 1,800 men worked throughout the interconnected complex. Dust lined the galleries. Ventilation moved air through the network. The gap between what operators believed and what the physical system contained was complete. All that remained was for ignition to bridge that gap and to reveal in the span of seconds just how wide it had been. At approximately 6:34 in the morning on March 10, 1906, the gap between operational perception and physical reality closed with violent finality. The transition from stable monitoring to catastrophic failure occurred not over hours or minutes, but over seconds, a time frame so compressed that no human response was possible, no alarm could be transmitted, no evacuation could be initiated. The initiating event was not a dramatic equipment failure or an obvious operational error. It was the inevitable intersection of conditions that had been assembling, unrecognized, for days. The precise ignition mechanism remains a matter of technical reconstruction rather than direct observation, because no witnesses to the initial event survived to provide testimony. Post-disaster analysis identified the most probable sequence. The fire that had been burning in the Cecile Gallery of Pit 3 since March 7 interacted with an accumulation of fire damp, methane released from the surrounding coal seams, creating a localized gas explosion. This initial explosion, while significant, was not itself catastrophic. Fire damp explosions had occurred in coal mines throughout history, causing casualties but rarely destroying entire operations. What made the Courrières event categorically different was what happened in the milliseconds following the initial ignition. The fire damp explosion generated a pressure wave and a flame front that propagated outward from the ignition point. As this wave traveled through the gallery, it encountered the coal dust that had accumulated on every surface: floors, walls, timber supports, equipment, rail lines. The pressure wave lifted this settled dust into suspension, creating a fuel-air mixture throughout the gallery volume. The flame front, following microseconds behind the pressure wave, ignited this newly suspended dust. The dust deflagration released energy that generated additional pressure, lifting more dust further along the gallery, which was in turn ignited by the advancing flame front. This self-sustaining mechanism, pressure wave suspending dust, flame front igniting suspended dust, combustion generating pressure that suspends more dust, is the defining characteristic of a coal dust explosion. Unlike a fire damp explosion, which consumes a finite volume of accumulated gas and then extinguishes, a dust explosion feeds on the fuel distributed throughout the mine's infrastructure. The explosion propagates as long as it continues to encounter sufficient dust concentration, sufficient oxygen, and pathways through which the pressure wave can travel. At Courrières, those pathways extended over 110 kilometers. The propagation velocity of a coal dust deflagration exceeds 300 meters per second under favorable conditions. This is faster than sound travels through the mine atmosphere, meaning that the pressure wave arrived at distant locations before any acoustic warning could reach them. Workers in galleries kilometers from the ignition point had no sensory indication that anything was wrong until the blast wave itself arrived. The event moved faster than human perception, faster than any communication system, faster than any conceivable response. Within the first seconds, the explosion had propagated through the connecting galleries between Pit 3 and Pits 24 and 10. The same network connectivity that enabled efficient ventilation and coal transport provided unobstructed pathways for the advancing pressure front. There were no barriers to close, no isolation points that could segment the network, no mechanism by which any part of the complex could be protected from an event originating in any other part. The design that optimized normal operations created catastrophic vulnerability to abnormal events. The physical effects of the propagating explosion varied with distance and geometry. Workers near the ignition point experienced the full force of the blast wave, overpressures sufficient to cause immediate fatal trauma, flame temperatures sufficient to cause lethal burns, complete destruction of timber supports and equipment. Workers at intermediate distances experienced reduced blast effects but remained exposed to the pressure wave, flying debris, and the immediate atmospheric consequences of the explosion. Workers at greater distances, in galleries not directly in the propagation path, were initially shielded from blast effects. But survival of the initial blast was not survival of the event. The explosion consumed the oxygen in every gallery through which it propagated, replacing breathable atmosphere with the products of combustion. These products, collectively termed afterdamp, consisted primarily of carbon monoxide, carbon dioxide, nitrogen, and residual particulates. Carbon monoxide is the critical component. It is lethal at concentrations above 0.1%, it is colorless and odorless, and its physiological effects do not provide warning before incapacitation. Miners who survived the blast found themselves in an atmosphere that was rapidly becoming unsurvivable. The ventilation system, designed to sustain life by providing continuous fresh air, now operated to distribute death. The explosion had disrupted normal airflow patterns, destroying ventilation doors, collapsing galleries, reversing pressure differentials, but the fans continued to operate and air continued to move through whatever pathways remained open. This moving air carried afterdamp from areas of high concentration to areas where miners had survived the initial blast. Workers in refuge areas, in galleries peripheral to the main propagation path, in sections that seemed initially unaffected, received lethal doses of carbon monoxide through the same airways that normally delivered their oxygen supply. The divergence between surface perception and underground reality was immediate and absolute. Surface personnel experienced the explosion as a series of effects. A muffled concussion transmitted through the ground, a sudden change in ventilation fan behavior as pressure differentials shifted, the appearance of smoke and debris at shaft openings. These effects indicated that something significant had occurred underground, but they provided no information about the scale or extent of the event. The assumption framework that underground incidents were localized shaped initial interpretation. The first response was to determine which pit had experienced a problem, not to assume that all pits were simultaneously affected. The shaft infrastructure itself provided misleading signals. Pit 3, where the fire had been monitored and where the explosion originated, showed the most dramatic surface effects: smoke billowing from the shaft, debris ejected by the pressure wave, clear evidence of severe underground damage. The other pits showed less dramatic effects initially, suggesting to surface observers that the event might be contained to Pit 3. This interpretation was logical given the information available, but catastrophically wrong. The underground network was a single connected atmospheric volume. An event sufficient to produce the observed effects at Pit 3 had already propagated throughout the system. The communication limitations that had prevented warning before the explosion now prevented accurate assessment afterward. Signal bells from underground were silent. The signaling infrastructure had been destroyed, or the personnel who operated it were dead or incapacitated. No reports arrived from pit bottoms because there was no one capable of sending them. Surface supervisors could see effects but could not determine causes. They knew something catastrophic had happened at Pit 3. They did not yet understand that the same catastrophe had happened everywhere. The first rescue attempts reflected this incomplete understanding. Teams prepared to descend Pit 3 to assess damage and locate survivors, operating on the assumption that other pits might be available as alternative access routes or refuge areas. The discovery that all 4 pits had been affected, that the entire underground complex was compromised, emerged gradually as rescue parties encountered the same conditions at every entry point: destroyed infrastructure, unbreathable atmosphere, evidence of explosion throughout the workings. For the miners underground, the divergence between perception and reality took a different form. Those who survived the initial blast and remained conscious found themselves in an environment that provided almost no useful information about their situation. Visibility was zero or near zero due to suspended dust and smoke. Familiar landmarks, gallery intersections, equipment locations, ventilation doors were destroyed or displaced. The darkness was complete. The explosion had extinguished safety lamps, and no miner would risk relighting a flame in atmosphere of unknown composition. Navigation became impossible. Miners who knew the galleries intimately under normal conditions could not orient themselves in the post-explosion environment. The mental maps that enabled efficient movement through the mine were rendered useless when the physical features those maps referenced no longer existed. Survivors who attempted to move toward pit bottoms, the only route to surface and safety, had to navigate without visual reference, without reliable knowledge of which passages remained open, and without any way to assess whether the air they were breathing was survivable. The afterdamp compounded this disorientation. Carbon monoxide poisoning produces symptoms that impair judgment before they impair mobility, confusion, headache, impaired reasoning, difficulty concentrating. Some miners attempting to make survival decisions, which direction to move, whether to conserve energy or press forward, whether to seek refuge or continue toward the shaft, were making those decisions with progressively compromised cognitive function. The atmosphere was not merely lethal, it was deceptive, impairing the mental capacity needed to escape before it incapacitated the body entirely. Some miners recognized the atmospheric danger and attempted to create improvised refuges, sealing themselves into relatively intact galleries using debris, clothing, or any available material to reduce air exchange with the contaminated main airways. This response reflected survival instincts and, in some cases, training for fire damp emergencies. But the strategy that might preserve life during a localized fire damp incident was less effective against network-wide atmospheric contamination. Sealed refuges provided temporary protection, but the atmosphere outside was not clearing. The explosion had contaminated the entire system, and the ventilation infrastructure that might have restored breathable air was too damaged to function normally. The timeline of the underground environment during the first hours after the explosion can only be reconstructed inferentially. No clocks survived, no logs were kept, and survivors' testimony from those few who were eventually rescued was fragmented by trauma and the cognitive effects of carbon monoxide exposure. What is known is that the transition from survivable to lethal atmosphere occurred rapidly in most areas, and that miners who were not killed by the blast itself faced a narrowing window of opportunity to reach breathable air. The physics of the situation were unforgiving. Carbon monoxide is slightly lighter than air but mixes readily with other atmospheric gases. It does not stratify in a way that would allow miners to find safe breathing zones near the floor or ceiling. The concentrations produced by a coal dust explosion are far above the lethal threshold, meaning that even brief exposure without respiratory protection is sufficient to cause death. The volume of afterdamp generated by the combustion of dust throughout over 100 kilometers of gallery exceeded any possibility of rapid dilution, even if ventilation had been functioning normally. The point of divergence, the moment at which underground reality separated from surface understanding and, more importantly, from any possible intervention, occurred within the first minutes after ignition. By the time surface personnel recognized that a major event had occurred, the atmospheric conditions underground had already determined who would live and who would die. The propagation velocity of the explosion meant that miners at the far end of the network died almost simultaneously with miners near the ignition point. The distribution of afterdamp meant that miners who survived the initial blast had only minutes to reach uncontaminated atmosphere before carbon monoxide levels became lethal. The scale of fatality was not determined by the force of the explosion alone. It was determined by the intersection of explosion physics, network geometry, ventilation behavior, and atmospheric chemistry. Each of these factors operated according to well-understood physical principles. Together, they created an outcome that exceeded any scenario for which the system had been designed or personnel had been trained. The surface response that followed, the rescue attempts, the secondary hazards, the agonizing uncertainty about who might still be alive, unfolded against this physical backdrop. Every decision made by rescue coordinators, every risk taken by rescue teams, every hope held by waiting families was constrained by conditions established in the first seconds after ignition. The failure chain was complete before any response could begin. What remained was the long, painful process of discovering what the physics had already determined. The physical processes that unfolded in the Courrières complex during and after the explosion operated according to principles that were, in 1906, understood in laboratory settings but rarely observed at industrial scale. Reconstructing the failure chain requires tracing how energy, pressure, mass, and chemistry interacted across a network of galleries that had been designed without consideration for the forces now moving through them. The disaster was not a single event, but a cascade of physical phenomena, each creating conditions that enabled or amplified the next. The initiating fire-damp explosion released energy estimated in the range of several hundred kilograms of TNT equivalent, significant but not unprecedented for underground methane ignitions. This energy manifested as a rapidly expanding pressure wave and an associated flame front. The pressure wave traveled outward from the ignition point at velocities approaching the speed of sound in the mine atmosphere, approximately 340 meters per second. The flame front followed at somewhat lower velocity, limited by the combustion rate of the methane-air mixture. In a mine without accumulated coal dust, this explosion would have caused localized destruction near the ignition point, with effects diminishing rapidly as the pressure wave expanded and dissipated through the gallery network. Casualties would have been concentrated in the immediate vicinity of the explosion. The event would have been serious but bounded, consistent with the incident scale for which emergency procedures had been developed. The presence of coal dust transformed the physics entirely. As the pressure wave from the initial fire-damp explosion traveled through the galleries, it interacted with dust that had accumulated on every available surface. The aerodynamic forces associated with the pressure wave, turbulence, shear, and the rapid pressure changes themselves, lifted this settled dust into suspension. Within milliseconds of the pressure wave's passage, the gallery atmosphere transitioned from relatively clear air with dust on surfaces to a dense suspension of combustible particles. The flame front, arriving microseconds after the pressure wave, encountered this newly created fuel-air mixture. Coal dust suspended in air at concentrations above the lower explosive limit, approximately 40 grams per cubic meter, ignites readily and burns rapidly. The combustion of this suspended dust released additional energy, generating a secondary pressure wave that traveled ahead of the expanding flame front, suspending more dust, which was in turn ignited. This self-reinforcing mechanism converted a finite fire-damp explosion into a propagating dust deflagration limited only by the availability of fuel, oxygen, and propagation pathways. The energy release from coal dust combustion far exceeded that of the initiating fire-damp explosion. Each kilogram of coal dust, fully combusted, releases approximately 33 megajoules of energy. The galleries of the Courrières complex contain dust accumulations measured in tons distributed over 110 kilometers of passageway. Even partial combustion of this material released energy equivalent to thousands of kilograms of explosive, an order of magnitude beyond the initiating event and beyond any scenario contemplated in mine design or emergency planning. The propagation dynamics of the dust explosion were shaped by gallery geometry. In straight passages with uniform cross-section, the deflagration could accelerate toward detonation velocities as the pressure wave became increasingly coupled with the combustion front. In passages with varying geometry, intersections, changes in cross-section, bends, the explosion behavior became more complex with reflections, turbulence, and localized pressure intensification. The connecting galleries between pits, designed for haulage and ventilation, provided relatively unobstructed pathways that allowed the explosion to maintain coherence as it propagated through the network. The ventilation infrastructure interacted with the explosion in ways that amplified its effects. Ventilation doors, designed to control airflow patterns under normal conditions, were destroyed by the pressure wave, eliminating any possibility of compartmentalizing the atmospheric consequences. Ventilation shafts, which under normal conditions provided controlled pathways for air movement, now served as chimneys through which pressure could vent and through which fresh air could potentially feed ongoing combustion. The fans themselves, continuing to operate at the surface, created pressure differentials that influenced how atmospheric conditions evolved in the post-explosion environment. The mass balance of the event illustrates why the atmospheric consequences were so severe. The explosion consumed oxygen throughout its propagation path, oxygen that would otherwise have supported human respiration. The combustion products replaced this oxygen with gases that were not merely non-breathable but actively toxic. Carbon monoxide, produced by incomplete combustion of coal dust, accumulated to concentrations lethal within minutes of exposure. Carbon dioxide, a product of more complete combustion, accumulated to levels that would cause unconsciousness, even in the absence of carbon monoxide. The residual atmosphere, nitrogen, from the original air, combustion products, and residual particulates, could not sustain human life. The distribution of these toxic products through the gallery network determined the pattern of fatalities. Miners near the explosion path died from a combination of blast trauma, thermal injury, and immediate atmospheric exposure. Miners at greater distances, shielded from direct blast effects, died from carbon monoxide poisoning as afterdamp reached their locations through connecting galleries and airways. The ventilation system, partially functional despite the damage, continued to move air through the network, but this air movement distributed poison rather than oxygen. The physics of carbon monoxide poisoning made survival time critically short. Carbon monoxide binds to hemoglobin with an affinity approximately 240 times greater than oxygen. Once inhaled, it rapidly displaces oxygen from the bloodstream, causing cellular hypoxia even when the lungs are functioning normally. Symptoms progress from headache and confusion at low concentrations through impaired coordination and judgment at moderate concentrations to unconsciousness and death at high concentrations. The concentrations present in the Courrières galleries after the explosion, estimated from combustion calculations and consistent with the pattern of fatalities, would have caused incapacitation within minutes and death shortly thereafter. The thermal effects of the explosion, while less extensive than the atmospheric effects, contributed to the immediate casualty toll. Coal dust combustion generates flame temperatures sufficient to cause fatal burns on contact. Miners in the direct path of the flame front received thermal injuries in addition to blast trauma. The heat also ignited secondary fires in timber supports, coal accumulations, and other combustible material throughout the affected galleries, creating ongoing combustion that continued to degrade atmospheric conditions even after the primary explosion front had passed. The physical damage to the mine infrastructure created additional hazards and complicated any possibility of rescue. Roof falls occurred throughout the affected areas as timber supports were destroyed by the pressure wave or burned by the flame front. These collapses blocked galleries, trapped miners who might otherwise have escaped, and created hazardous conditions for any personnel attempting to enter the mine afterward. Haulage equipment, coal cars, rail lines, winching systems was displaced and destroyed, eliminating the transportation infrastructure that would normally facilitate emergency response. The pressure dynamics of the explosion produced effects at significant distances from the combustion front. Pressure waves traveling through the gallery network were reflected at dead ends, amplified at constrictions, and refracted at intersections. These interactions created pressure transients that could cause injury or structural damage in locations not directly affected by the flame front. Miners in peripheral galleries might have experienced damaging overpressure without direct exposure to the combustion products, though such survival would have been temporary given the subsequent atmospheric deterioration. The 4 pits of the Courrières complex experienced the explosion nearly simultaneously due to their interconnection. The propagation time from the ignition point in Pit 3 to the most distant workings of Pits 24 and 10 was measured in seconds, far less than any possible warning or evacuation time. By the time surface personnel observed the first effects at Pit 3, the explosion had already propagated through the connecting galleries and was manifesting at all 4 pit locations. The assumption that the event was localized to Pit 3, a reasonable interpretation of the initial surface observations, was invalidated by the physics of propagation before it was even formulated. The point at which the disaster became irreversible occurred essentially instantaneously with the initiating ignition. Once the fire damp explosion lifted sufficient dust into suspension to sustain a propagating deflagration, the outcome was determined by physics rather than human action. No intervention was possible at the timescale required. The miners who would die were already exposed to lethal conditions before any surface alarm could be raised, before any evacuation order could be issued, before any rescue could be contemplated. The failure chain was complete within the first minute. This physical reality defines the forensic challenge of the Courrières disaster. Unlike accidents that unfold over extended periods, where intervention points exist, where decisions might have changed outcomes, where human factors interact with developing events, the Courrières explosion compressed the entire causal sequence into a time frame that admitted no response. The decisions that determined the outcome were made in the days and years before March 10th, decisions about mine design, about dust accumulation, about fire management, about training and procedures. By the morning of the disaster, all that remained was for the latent conditions to be actualized by an ignition event. The physics of the explosion also determined what rescue efforts could and could not accomplish. The atmospheric conditions underground were lethal throughout the connected network. Any rescue party entering the mine would encounter the same afterdamp that had killed the miners they were attempting to save. Without respiratory protection capable of sustained operation in carbon monoxide concentrations measured in percentages rather than parts per million, rescue was not merely difficult but impossible. The technology to safely enter such an environment existed in 1906 only in limited forms, not widely deployed, and not available at Courrières in the quantities or configurations required. The feedback loop between the physical failure and the information environment deserves explicit attention. The explosion destroyed the infrastructure that might have reported underground conditions to the surface. The miners who might have signaled for help were dead or incapacitated. The communication systems that might have transmitted warnings were themselves casualties of the event they were needed to report. The surface response operated with minimal information precisely because the event had eliminated the sources of information. This information void shaped every subsequent decision, ensuring that rescue efforts would proceed without accurate knowledge of what they were attempting to address. The final physical state of the mine after the explosion reflected the energy that had passed through it. Galleries were collapsed or blocked. Ventilation patterns were disrupted beyond recognition. Atmospheric conditions varied by location but were uniformly hazardous. Secondary fires burned in scattered locations. The infrastructure that had supported extraction operations was destroyed or damaged beyond immediate use. The mine was not merely a disaster site, it was an environment hostile to human survival, hostile to investigation, hostile to any activity other than patient, cautious recovery over extended timeframes. Understanding this physical reality is essential to evaluating the response that followed. The rescue attempts, the secondary casualties among rescuers, the agonizing delays in reaching survivors, the ultimate discovery that some miners had survived for days in isolated pockets. All of these developments occurred within constraints established by the physics of the explosion. The decisions made by rescue coordinators were not made in a vacuum of option space. They were made within boundaries defined by atmospheric chemistry, structural stability, and the limitations of available protective equipment. The next phase of analysis must examine how human response interacted with these physical constraints and why the gap between hope and reality proved so difficult to close. The surface response to the Courrières explosion began within minutes of the event, but operated throughout under constraints that made effective intervention nearly impossible. The gap between the urgency of the situation and the capability to address it defined the rescue effort, a sustained attempt to save lives in an environment that had already determined, through physics and chemistry, who could be saved and who could not. The responders were not incompetent or indifferent. They were confronting conditions that exceeded the technological and organizational capacity of their era. The first surface indications of the disaster were ambiguous. Personnel at Pit 3 observed smoke and debris ejecting from the shaft, accompanied by a pressure pulse that disrupted ventilation fan operation. The immediate interpretation was that an explosion had occurred underground at Pit 3, a serious event requiring emergency response, but based on experience with previous incidents, potentially localized and containable. The initial mobilization focused on Pit 3, assembling rescue teams, preparing descent equipment, and attempting to establish communication with underground personnel. Within the first hour, it became apparent that the event was not localized. Similar effects were observed at Pits 2, 4, and 10: smoke, pressure disturbances, silence from underground. The realization that all 4 pits had been affected simultaneously transformed the response from a single pit emergency to a complex-wide catastrophe. The organizational structures designed for localized incidents were overwhelmed by an event that required coordinated action across multiple locations with multiple entry points, all of which were compromised. The first rescue parties descended into conditions they were not equipped to survive. The respiratory protection available to Courrières rescue teams in 1906 was primitive by modern standards. Self-contained breathing apparatus existed. The Draeger oxygen apparatus had been developed in Germany and was used in some mining operations, but was not widely deployed in French mines and was not available at Courrières in sufficient quantities for large-scale rescue operations. Most rescuers entered the mine with only flame safety lamps, which provided no respiratory protection and could not reliably indicate carbon monoxide presence. The consequences were immediate and tragic. Rescue parties descending the shafts encountered afterdamp at concentrations sufficient to cause rapid incapacitation. Rescuers who entered without breathing apparatus collapsed within minutes. Those who recognized the atmospheric danger and retreated did so with partial carbon monoxide exposure, experiencing symptoms that impaired their ability to report accurately on underground conditions. The first rescue attempts produced additional casualties without reaching any survivors. The atmospheric monitoring capability available to rescue coordinators was inadequate to characterize the underground environment. Flame safety lamps could detect fire damp, methane, but carbon monoxide is not flammable at concentrations below 12%, far above the lethal threshold. The primary lethal agent in the afterdamp was therefore invisible to the primary detection tool. Canaries and mice, used in some mining operations as biological indicators of atmospheric hazard, could detect carbon monoxide through their physiological response, but their sensitivity varied and their signals were difficult to interpret quantitatively. Rescuers knew the atmosphere was dangerous. They could not determine how dangerous, where the boundaries of the hazard lay, or how conditions were evolving over time. The decision-making framework for rescue operations reflected this uncertainty. Rescue coordinators faced a cruel optimization problem. Aggressive entry might reach survivors, but would certainly expose rescuers to lethal conditions. Conservative delay would protect rescuers, but might abandon survivors who could be saved. Without reliable information about atmospheric conditions at various depths and locations, this trade-off could not be resolved rationally. Decisions were made based on hope, courage, and the imperative to attempt rescue, rather than on calculated risk assessment. The secondary explosion risk compounded the atmospheric hazard. The initial disaster had not consumed all combustible material in the mine. Residual methane continued to seep from coal seams. Pockets of unburned coal dust remained in galleries not directly affected by the flame front. Smoldering fires, ignited by the explosion, continued to burn in timber and coal accumulations. The introduction of fresh air through rescue shafts or through reopened ventilation pathways could create conditions for secondary explosions, a hazard that had killed rescue teams in previous mining disasters. This risk created additional constraints on rescue operations. Aggressive ventilation to clear afterdamp might introduce oxygen that would feed smoldering fires or create explosive atmospheres. Sealing the mine to starve fires of oxygen would abandon any survivors who might be sheltering in breathable pockets. The physical chemistry of the post-explosion environment presented no good options, only choices among different categories of unacceptable risk. The organizational response expanded rapidly as the scale of the disaster became apparent. Mining engineers, rescue specialists, and officials from surrounding operations converged on Courrières. Equipment was transported from other facilities. The French government mobilized military resources to support rescue and recovery operations. International attention focused on the disaster site as news spread of the unprecedented casualty toll. This mobilization brought additional resources, but also additional complexity, coordination challenges, conflicting authorities, and the logistical burden of managing large numbers of personnel in a chaotic environment. The rescue teams that achieved penetration into the mine did so through a combination of improved equipment, careful atmospheric assessment, and acceptance of significant personal risk. Draeger apparatus and similar self-contained breathing equipment were obtained from German suppliers and other sources, enabling rescuers to operate in atmospheres that would otherwise be immediately lethal. These devices provided limited duration, typically 30 minutes to 2 hours of operation, depending on the specific apparatus and exertion level, constraining how far into the mine rescue parties could penetrate and how long they could remain. The conditions encountered by rescue parties who successfully entered the mine confirmed the catastrophic scope of the event. Bodies were found throughout the workings, at pit bottoms, along haulage routes, in refuge areas, at gallery intersections. The distribution of fatalities reflected the physics of the explosion and its aftermath: blast trauma near the propagation path, carbon monoxide poisoning at greater distances, evidence of attempted escape and shelter-seeking behavior. Many victims showed no external injuries, consistent with death from atmospheric exposure rather than mechanical trauma. The discovery pattern revealed how rapidly lethal conditions had developed. Miners were found in positions suggesting sudden collapse, mid-stride, seated at workstations, slumped against walls. The carbon monoxide had incapacitated them before they could complete purposeful movement toward escape. Others were found in groups, having congregated at familiar locations or attempted collective escape. The social organization of the work crews remained visible in death, with miners found near their usual work partners and supervisors found near their usual stations. Some evidence suggested survival periods longer than the immediate aftermath. Miners were found in sealed areas, having constructed barriers from available materials in apparent attempts to create breathable refuges. Food containers were found emptied. Messages were found scratched into walls or written on available surfaces. These findings indicated that some miners had survived the initial event and the immediate atmospheric crisis, sheltering in pockets where breathable air persisted longer than in the main galleries. The rescue effort was therefore not merely a recovery operation, but potentially a life-saving mission, if survivors could be located before their refuges became untenable. This possibility drove continued rescue efforts despite the ongoing hazards and the mounting evidence of mass casualties. The uncertainty about whether survivors remained underground created moral pressure to continue operations that might otherwise have been suspended on safety grounds. Each day without contact increased the probability that any survivors had succumbed, but could not reduce that probability to zero. Rescue coordinators operated in a state of sustained uncertainty, unable to confirm that the effort was futile, but increasingly doubtful that it could succeed. The atmospheric conditions in the mine evolved over the days following the explosion, but did not quickly become survivable. Afterdamp persisted in galleries where ventilation had been disrupted. Secondary fires continued to consume available fuel and degrade air quality. Structural instability from blast damage and fire effects created ongoing collapse hazards. The mine environment remained hostile to human presence, requiring rescue teams to operate in full protective equipment for every penetration and limiting the depth and duration of search operations. The decision to seal certain sections of the mine represented one of the most difficult judgments faced by rescue coordinators. Sealing could extinguish fires by removing oxygen, stabilize atmospheric conditions, and reduce secondary explosion risk. But sealing also meant abandoning any hope of reaching survivors in the sealed areas, a decision that could not be made with certainty about whether survivors existed. The ethical weight of these decisions fell on individuals operating with incomplete information under extreme time pressure, knowing that either choice might result in preventable death. 13 days after the explosion, on March 23rd, a group of 13 survivors was discovered in a remote section of the mine. These men had sheltered in a gallery where atmospheric conditions had remained marginally survivable, sustaining themselves on water seepage, a dead horse, and whatever food they had carried. Their survival demonstrated that breathable pockets had persisted in the mine far longer than the general atmospheric conditions suggested, and raised agonizing questions about whether other survivors might have existed in other locations, unreached before their refuges failed. The discovery of the 13 survivors transformed the rescue effort, demonstrating that survival was possible and reinvigorating search operations. Additional resources were committed. Search protocols were revised to focus on identifying other potential refuge areas. The mine was systematically explored to the extent that atmospheric and structural conditions permitted. 7 days later, on March 30th, an additional group of survivors emerged, not rescued by search parties, but having made their own way to the surface through galleries that had become navigable as atmospheric conditions slowly improved. This group of survivors, though smaller, provided additional evidence that survivable conditions had persisted in scattered locations throughout the mine. The total survivor count, 20 miners from an underground population of over 1,800, represented both a miracle and an indictment. A miracle because survival for 20 days in a collapsed, poisoned mine environment exceeded any reasonable expectation. An indictment because the rescue effort, despite enormous commitment and sacrifice, had not located these survivors. They had survived despite the rescue operation rather than because of it. The limitations of atmospheric detection, breathing apparatus duration, and search methodology had prevented rescue teams from finding the very survivors whose possible existence had justified the continued effort. The final casualty toll of 1,099 deaths made Courrières the deadliest mining disaster in European history. This number represented not merely the victims of the explosion itself, but the victims of the entire failure chain, design decisions that created network-wide vulnerability, operational decisions that permitted dangerous conditions to develop, the initiating event that triggered the catastrophe, and the limitations of response capability that prevented effective intervention. Each death represented a human being whose survival was foreclosed by systemic factors established long before March 10, 1906. The rescue operation continued for weeks, transitioning gradually from life-saving search to body recovery. The physical and psychological toll on rescue personnel was severe. Many had been exposed to carbon monoxide at sublethal concentrations, experiencing persistent symptoms of poisoning. Many had witnessed scenes of mass death that would mark them for life. The rescue effort itself produced casualties, rescuers who died from atmospheric exposure, structural collapse, or secondary explosion. The attempt to mitigate the disaster had extended its reach. The stabilization of the mine environment occurred gradually over the following months. Fires were extinguished or allowed to burn themselves out. Ventilation was partially restored. Atmospheric monitoring eventually confirmed that conditions had become survivable in most accessible areas. The physical infrastructure of the mine was assessed for potential restoration, though the scale of damage made full recovery a long-term proposition. Throughout this period, the gap between what had been hoped and what had been achieved remained stark. The rescue effort had been mounted with commitment, courage, and all available resources. It had saved no lives that would not have been saved by the survivors' own efforts. The technological and organizational limitations of 1906 mining safety had been exposed with brutal clarity. The question of what could have been done differently haunted everyone involved. A question that would drive the forensic investigation and regulatory response that followed. The forensic investigation of the Courrières disaster began while rescue operations were still underway and continued for months after the last body was recovered. The challenge facing investigators was not merely to determine what had happened. The basic sequence of events was apparent from the physical evidence, but to understand why it had happened, what systemic factors had contributed to the catastrophic outcome, and what changes could prevent similar disasters in the future. The investigation produced findings that transformed mining safety practice not only in France, but throughout the industrialized world. The physical evidence recovered from the mine told a story consistent with the theoretical reconstruction of coal dust explosion mechanics. The distribution of blast damage, destroyed timber supports, displaced equipment, collapsed galleries, traced the propagation path of the explosion through the network. The damage patterns showed intensification at certain points, consistent with pressure wave reflection and amplification at gallery intersections, and changes in cross-section. The extent of damage throughout all four interconnected pits confirmed that the explosion had propagated through the entire network, rather than remaining localized at its origin point. The forensic examination of fatalities provided additional evidence about the failure mechanism. Autopsies performed on recovered bodies revealed the characteristic cherry-red coloration of carbon monoxide poisoning in the majority of victims. This finding confirmed that afterdamp, rather than blast trauma, was the primary cause of death for miners located at distance from the explosion's propagation path. The medical evidence aligned with the physical evidence. The explosion had killed some victims directly, but its atmospheric consequences had killed far more. The investigation of the initiating event focused on the fire in Pit 3 that had been burning since March 7. Investigators reconstructed the fire's location, extent, and management through interviews with surviving supervisors and examination of records and physical evidence. The fire had been monitored but not extinguished, consistent with standard practice for underground fires that appeared contained. The decision to continue operations during the fire was documented and explicable within the framework of existing procedures. The critical finding was that the fire's interaction with accumulated fire damp and coal dust had not been anticipated by those managing the situation. The monitoring protocol focused on the fire's visible characteristics, size, smoke production, apparent trajectory, rather than on the atmospheric conditions in surrounding galleries. No measurement had been made of dust concentrations in the areas adjacent to the fire. No assessment had been made of whether ventilation patterns might be transporting combustible dust toward the heat source. The information framework within which decisions were made excluded the mechanism that ultimately caused catastrophic failure. Investigators examined the coal dust conditions throughout the affected areas. The evidence was unambiguous. Dust accumulation in the Courrières galleries had been extensive, particularly along haulage routes where coal transportation generated continuous dust production. Samples collected from unaffected areas showed dust concentrations well above the threshold required for explosive propagation. The mine had been operating with an explosive fuel-air mixture distributed throughout its infrastructure, unrecognized as a hazard because the safety framework focused on fire damp rather than dust. The ventilation system design received detailed forensic attention. Investigators mapped the network of airways, shafts, and connecting galleries, documenting how the interconnected architecture had enabled explosion propagation. They identified the absence of barriers or isolation mechanisms that might have limited the event's geographic scope. The design philosophy, optimization for fire damp dilution through continuous through-flow, was documented as a contributing factor to the disaster's scale. The features that made the ventilation system effective under normal conditions were the same features that made it catastrophically vulnerable under abnormal conditions. The investigation also examined the regulatory and institutional context in which the Courrières operation functioned. French mining regulations of the era focused primarily on fire damp management, reflecting the historical experience, with methane explosions as the dominant underground hazard. Requirements for dust control were minimal or non-existent. Inspection protocols did not include systematic assessment of dust accumulation. The regulatory framework, like the operational framework, was calibrated to a hazard model that excluded the mechanism responsible for the disaster. The training and qualification standards for mining personnel were similarly examined. Investigators found that fire damp awareness was emphasized in miner training, while coal dust explosion hazards received little or no attention. Supervisory personnel were trained to recognize and respond to methane accumulation, but were not equipped to assess dust explosion risk. The knowledge gap identified at the operational level reflected a knowledge gap at the training and regulatory levels, a systemic failure to translate scientific understanding of dust explosivity into operational practice. The investigation confronted the question of whether the disaster could have been prevented given the state of knowledge in 1906. This question admitted no simple answer. The explosivity of coal dust was documented in scientific literature. Laboratory experiments had demonstrated the conditions required for dust deflagration. Some mining operations in other countries had implemented dust suppression measures based on this research. The knowledge existed, its application to the Courrières operation did not. Investigators identified several intervention points where different decisions might have prevented or mitigated the disaster. Systematic dust suppression, wetting or stone dusting, could have reduced dust accumulation below explosive thresholds. Ventilation barriers capable of rapid closure could have limited explosion propagation between pit sectors. The fire in Pit 3 could have been treated with greater urgency, prompting evacuation or more aggressive suppression efforts. Each of these alternatives was technically feasible in 1906, but was not implemented because the existing framework did not identify them as necessary. The assignment of responsibility for the disaster proved contentious. Mining company management had operated within established procedures and regulatory requirements. Supervisory personnel had made decisions consistent with their training and the information available to them. Regulatory authorities had enforced standards that were considered adequate before March 10th. No individual had acted with negligence or reckless disregard for safety. The disaster emerged from systemic gaps rather than individual failures. This finding was unsatisfying to those seeking accountability, but was consistent with the forensic evidence. The public and political response to the investigation findings was intense. The death of over 1,000 miners in a single event produced outrage that demanded both explanation and reform. Labor organizations already active in the French mining industry used the disaster as evidence of management indifference to worker safety and as justification for improved working conditions and stronger worker protections. The investigation became intertwined with broader social and political conflicts that shaped the public interpretation of its findings. Strikes and civil unrest followed the disaster, driven by a combination of grief, anger, and long-standing labor grievances. The response of authorities to these disturbances added additional casualties to the disaster's toll. The social consequences of the Courrières explosion extended far beyond the immediate fatalities, affecting labor relations, political dynamics, and public trust in industrial safety for years afterward. The regulatory response to the investigation findings was substantial. French mining law was revised to address the specific failures identified in the investigation. Mandatory dust suppression became a requirement in coal mines, with stone dusting, the application of powite calcium powder to render coal dust inert, specified as the preferred method. Ventilation standards were strengthened to require compartmentalization capabilities that could limit explosion propagation. Fire management protocols were revised to emphasize evacuation over continued operations when underground fires were detected. Rescue and emergency response capabilities received particular attention. The investigation had documented the inadequacy of respiratory protection available to Courrières rescue teams. In response, regulations were established requiring mining operations to maintain self-contained breathing apparatus in quantities sufficient for rescue operations. Training requirements for rescue personnel were strengthened. The development and deployment of improved atmospheric monitoring equipment was encouraged. The international impact of the Courrières investigation extended the disaster's influence beyond French borders. Mining engineers and safety officials from Britain, Germany, Belgium, the United States, and other coal-producing nations studied the findings and implemented similar reforms in their own jurisdictions. The disaster became a reference case in mining safety literature, cited in regulatory proceedings and engineering standards for decades afterward. The Courrières investigation effectively established coal dust explosion prevention as a foundational requirement of underground mining safety worldwide. The technical legacy of the disaster included specific engineering practices that became industry standards. Stone dusting, mixing limestone or calcium carbide powder with coal dust to raise the ignite temperature and reduce explosivity, was adopted throughout the global mining industry. Ventilation barrier design was revised to include rapid closure capabilities. Atmospheric monitoring requirements expanded to include dust concentration measurement alongside fire damp detection. These practices, derived directly from the Courrières investigation findings, prevented countless subsequent disasters by addressing the specific failure mechanisms the investigation had identified. The human factors findings of the investigation proved equally influential. The documentation of how training emphasis, information systems, and decision frameworks had channeled behavior toward catastrophic outcomes established principles that informed industrial safety analysis for generations. The concept that disasters emerge from systemic gaps rather than individual failures, that competent people following established procedures can produce catastrophic outcomes when those procedures are miscalibrated to actual hazards, became a foundational insight of safety science. The investigation also documented the limitations of post hoc analysis in attributing causation. Many aspects of the disaster sequence could not be definitively established because the evidence was destroyed or because no observers survived to provide testimony. The investigation acknowledged these uncertainties rather than constructing false certainty. This epistemic humility, the recognition that forensic reconstruction has limits, became itself a methodological lesson for subsequent disaster investigations. The physical recovery of the Courrières mine complex proceeded over several years. Some sections of the mine were abandoned permanently, their galleries too damaged or too dangerous to restore. Other sections were rehabilitated and returned to production, though never at the scale of pre-disaster operations. The mine eventually resumed extraction, but operated under the reformed regulatory regime that the disaster had precipitated. The physical site became a living laboratory for the safety improvements derived from its own catastrophic failure. The memorial response to the disaster reflected its scale and its impact on the affected communities. Mass graves received the unidentified dead. Monuments were erected to commemorate the victims. The anniversary of March 10, 1906, became a date of remembrance in the Pas-de-Calais region, observed with ceremonies that continued for generations. The disaster became embedded in the regional and national memory, a reference point for discussions of industrial safety, labor rights, and the human cost of resource extraction. The final forensic accounting of the Courrières disaster returns to the question posed at the outset: how does a ventilation system designed to sustain life become the primary mechanism for distributing death? The investigation provided the answer in technical detail. The ventilation system was designed for a specific hazard model, fire damp dilution, and optimized for efficiency within that model. The optimization created network connectivity that transmitted explosion effects throughout the system. The design assumptions that fires remain localized, that explosions remain bounded, that atmospheric hazards can be detected by human observation proved invalid when coal dust transformed a localized ignition into a propagating deflagration. The system did not fail because its designers were careless or its operators negligent. It failed because the information architecture embedded in its design, training, and procedures did not include the mechanism that caused the disaster. The ventilation network functioned exactly as designed. The design did not account for the physics of coal dust explosions. The operators made decisions consistent with their training. Their training did not address the hazard they faced. The emergency response deployed all available resources. Those resources were inadequate to the conditions produced by the event. The systemic lesson of Courrières is that safety depends not merely on following procedures but on ensuring that procedures are calibrated to actual hazards. The gap between the hazard model embedded in the Courrières operation and the hazard present in its physical environment was the fundamental cause of the disaster. Closing such gaps requires continuous effort, updating knowledge based on research and experience, translating new understanding into operational practice, and maintaining skepticism about the completeness of any hazard model. The 1,099 miners who died at Courrières did not die because of human failure in the conventional sense. They died because of a systemic gap between what was known about underground hazards and what was implemented in operational practice. Their deaths produced knowledge that saved countless future lives through the safety reforms that followed. This is the tragic paradox of disaster investigation, that prevention often follows catastrophe, that safety improvements are purchased with lives that better systems would have preserved. The Courrières disaster remains, over a century later, a foundational case in the study of industrial safety. Its lessons about the importance of complete hazard models, about the danger of optimizing for known risks while remaining blind to unknown risks, about the systemic nature of catastrophic failure, continue to inform safety practice across industries. The forensic record compiled in 1906 speaks across the decades to anyone responsible for designing, operating, or regulating systems where human lives depend on the completeness of the information architecture embedded in procedures and training. The mine is quiet now. The galleries that once carried the sounds of extraction, the voices of workers, and ultimately the roar of the explosion have been silent for generations. But the lessons extracted from that catastrophe continue to speak, embedded in safety codes and engineering standards and regulatory frameworks around the world. The deaths were not in vain if they produced understanding that prevents repetition. The forensic record exists so that the failure can be understood, and understanding can prevent recurrence. This is the purpose of disaster investigation, not to assign blame, though accountability has its place, but to extract from catastrophe the knowledge that makes future catastrophe less likely. The Courrières investigation accomplished this purpose. Its findings changed an industry. Its lessons transcended the specific technologies of coal mining to inform broader understanding of how complex systems fail and how such failures can be prevented. The information architecture that caused the Courrières disaster, the gap between the hazard present and the hazard perceived, is not unique to early 20th century French mining. It is a category of failure that recurs whenever systems are designed, operated and regulated based on incomplete models of the risks they face. The specific mechanisms change, the structural pattern persists. Recognizing this pattern is the enduring contribution of the Courrières investigation to the science and practice of safety.